Welcome to homework.
Hello everyone, today we're doing chapter 23, problem 44, and this problem asks us to draw the stepwise mechanism for each of these reactions. So here we have halogenation occurring, and in B we have some sort of acid-catalyzed halogenation, and what we know about acid-catalyzed halogenation, well, it starts off with two parts. Number one is going to be the enol keto tautomerization to form the enol form, and then once we have the enol form, we're going to use those pi electrons to act as a nucleophile to react with the halogen. So let's go ahead and start doing that. So we're going to start with our starting material here. And we're reacting it with some sort of acid here. So we have acetic acid and some ketone here. So what we know is that acetic acid is going to make the environment proton rich. So oxygen being having lone pair electrons and acting as a nucleophile is going to pick up one of these protons to protonate itself. So what you're going to have is now protonated oxygen with 3 bonds and the conjugate base of your acid. So now what can happen is that your acid catalyst wants to be reformed, so it's going to take off a proton off the alpha position. So now this conjugate base, being the nucleophile with lone pair electrons, are going to pick up this proton, making a bond. When you make a bond, you break a bond, so you're going to form the enol pi bond, making a bond. You make a bond, you want to break a bond, and the bond that's going to break is this pi bond on the oxygen nucleus, such that it's going to make oxygen have 2 bonds and neutralize itself. And now what we have is our enol tautomer, and we reform our acid catalyst. So at this point now, we're going to add our diatomic bromine, and using the enol as lone pair electron source, we're going to actually now, with this oxygen with those lone pair electrons, we're going to come back down to form the carbonyl bond, making a bond. You make a bond, you break a bond. So this alkene bond is going to go through this alpha carbon, and it's going to pick up a bromine nucleus. When you make a bond, you break a bond, so now that bromine-bromine bond breaks, and now you're forming again the carbonyl oxygen now with 3 bonds. Again, it's going to have a positive charge. Now you're forming a new bromine bond here, and then you have the bromide anion. So bromide anion in acidic conditions does not want to be anionic, it wants to be protonated. So it's going to pick up, being nucleophilic, it's going to pick up this acidic proton off this carbonyl oxygen to neutralize the entire system. And that's going to yield your final product in A. Now in B, it's a little different. So you can still have your iodines or your halogens, but now you're in basic conditions. So what you can say and see from the product here is that you're going to have some sort of haloform reaction. You're going to have essentially halogenation occurring, but then because we have halogens at this alpha position, those act as good leaving groups. So we're actually going to kick off this alkyl halide. We're just going to kick that off with our base that we're reacting these compounds in, and we're going to have a haloform being formed. So in haloform reaction, this alpha carbon here, the 3 protons of the alpha carbon are going to be successively replaced with the iodines. And once that, you're going to have oxidative or base-mediated cleavage occurring, such that you're going to have this haloform being formed with your alkyl halide and your negatively charged carboxylic acid or carboxylate anion. So how this occurs, so let's start with B. So B, we have the starting material. And now we're reacting this in basic conditions. So the base is going to rip off these less sterically hindered alpha carbons, alpha protons off the alpha carbons, take off one to form now an enolate. So those two electrons on that sigma bond between carbon and hydrogen are going to go into the carbon nucleus to form your enolate. Oh. So now you have an enolate being formed here. And at this point now, your enolate can react with I2 to form a new carbon halogen bond. When you make a bond, you break a bond. And then you have your first halogen added at this point. But you still have plenty of acid and plenty of diatomic halogen left. So what's going to happen is that you're going to have this whole process repeating 2 more times. So your base is going to rip off one of these protons. It's going to make your carbanion. Then your carbanion is going to act as a nucleophile to pick up the halogen. So you have a carbanion, and that's going to pick up another iodine. And then you're going to have dihalogenation occurring. And now this entire process is going to repeat 1 more time, such that you're going to have 3 iodines being added. So I'll just draw that product. So you're going to repeat the entire process again to now get 3 iodines being added. And now at this point now, you're going to have your base coming in, and you can oxidatively cleave this intermediate to form your haloform reagent. So what you're going to have is this alcohol coming in, attacking this electrophilic carbonyl carbon, making a bond. When you make a bond, you break a bond. So this carbonyl bond is going to break, go up to the oxygen nucleus, but then it's going to come back down to reform the carbonyl bonds. So now you made a new bond, so you got to kick off a bond. And what you kick off is a very good leaving group, being this alkyl halide here that we formed. And it's a very good leaving group because there's so much electron density being pulled towards the electronegative iodine atoms. And what you have here is now you're going to form a carbanion with 3 iodines. And obviously carbon is not happy being negatively charged, it'd rather be neutral. So it's going to rip off this acidic proton from this acid, which has a very low pKa, so it's actually very happy to give away that proton to carbon. And we're going to form the product in B, which is this carboxylate anion and our CHI3 byproduct.